Welcome all. Today we will learn about Zener Diode. On completion, students will be able to explain the working of Zener Diode and characteristics of Zener Diode. Zener Diode. Zener Diode is a reverse biased, heavily doped PN junction diode which operates in the breakdown region. The reverse breakdown of a PN junction may occur either due to Zener effect or avalanche effect. Zener effect dominates a reverse voltage less than 6 volt, whereas avalanche effect dominates above 6 volt. The breakdown voltage of Zener diode can be set by controlling the doping level. For Zener diode, silicon is preferred to germanium because of its high temperature and current capability. Forward biasing of Zener diode. When the anode of the Zener diode is connected to the positive terminal of the DC source and cathode is connected to the negative terminal, the Zener diode is said to be forward biased. The forward biased Zener diode behaves identical to a forward biased diode. Reverse bias of Zener diode. When the cathode is connected to the positive terminal and anode is connected to the negative terminal of the DC source, the Zener diode is said to be reverse bias. The operation of Zener diode in the reverse bias condition is different from that of diode. VI characteristics of Zener diode. Forward characteristics of Zener diode is identical to the forward characteristic of a PN junction diode. And next is reverse characteristics. As the reverse voltage is increased, initially a small reverse saturation current I naught, which is in microampere, will flow as shown in figure. This current flows due to the thermally generated minority carriers. At a certain value of reverse voltage, the reverse current will increase suddenly and sharply. This is an indication that the breakdown has occurred. The breakdown voltage is called as Zener breakdown voltage or Zener voltage. It is denoted by Vz. The value of Vz can be precisely controlled by controlling the doping level of P and N region at the time of manufacturing of Zener diode. After breakdown occurs, the voltage across Zener diode remain constant equal to Vz. Any increase in the source voltage will result in the increase in reverse Zener current. The Zener current after the reverse breakdown must be controlled by connecting a series resistor R. This is essential to avoid any damage to the device due to excessive heating. Zener breakdown is observed in the Zener diode having Vz less than 6 volt. When a reverse voltage is applied to a Zener diode, it causes a very intense electric field to appear across a narrow depletion region. Such an electric field is strong enough to pull some of the valence electron into the conduction band by breaking their covalent bonds. These electrons become free electrons which are available for conduction. A large number of such free electrons will constitute a large reverse current through the Zener diode, and breakdown is said to have occurred due to the Zener effect. The avalanche breakdown is observed in the Zener diode having Vz higher than 6 volt. In the reverse bias condition, the conduction will take place only due to minority carriers. As the reverse voltage is applied to Zener diode is increased, these minority carriers tend to accelerate. Now, these newly generated free electrons will accelerate. They will knock out some more valence electron by means of collision. This phenomenon is called avalanche multiplication, and in a short time a large number of free minority electrons and holes will be available for conduction, and the carrier multiplication process becomes self-sustained. The self-sustained multiplication is called avalanche effect. Diode as a voltage regulator. To maintain a constant voltage across the load, even if the input voltage or load current varies, voltage regulation is to be made. A Zener diode working in the breakdown region can act as voltage regulator. The circuit in which a Zener diode is used for maintaining a constant voltage across the load RL is shown in the figure. The Zener diode in reverse bias condition is connected in parallel with the load RL. Let VDC be the unregulated DC voltage and VZ be Zener voltage. RS is the current limiting resistor, and it is chosen in such a way that the diode operates in the breakdown region. The Diagram shows a circuit of Zener Diode shunt regulator. Since the Zener Diode is connected in parallel with the load, the circuit is known as shunt regulator. A resistance Rs is known as current limiting resistor. Rs is connected in series with the Zener to limit current in the circuit. Therefore, the output voltage is taken across the load resistance RL. For proper operation, the input voltage Vin must be greater than the Zener diode voltage. Zener's voltage regulator. Let us consider that the load current increases, Zener current hence decreases, and the current through the resistance Rs is a constant. The output voltage is Vz is equal to Vdc minus Irs. Since the total current I remains constant, output voltage remains constant. Second one is input voltage varies. Let us consider that input voltage VDC increases. Now the current through Zener increases and voltage drop across RS increases in such a way that the load voltage remains the same. Thus, the Zener diode acts as a voltage regulator.